Hello everyone, welcome back. Today we're going to learn about the chain rule. And this is what we use to help us take the derivative of complex functions, especially compound or um, composite functions. So our goal is then to be able to use the chain rule, learn what it is and how to use it. Also use something called U substitution, which will help us simplify complicated functions, write them in a way that's often easier to understand. And also we'll learn how we can use the product rule instead of the quotient rule by using the chain rule to help us out. First, let's talk about what the chain rule is, what it says. So the chain rule, so let's say we have a function, basically be a composite function, some function f of u, or u is our independent variable. Let's say that u itself is also a function of g, okay? And both functions differentiable, both they're both nice, you can take the derivative of them. Then if we have the composite function, hope you remember composite functions from your algebra classes, where it's basically a function inside another function. If we have a composite function like this, if we take the derivative of the whole thing, basically what it is, essentially we take the derivative first of f, and actually I realize I should have, I can correct this. Let me change this, call this f instead. There we go. Y is fine, we get the idea better. So first off, basically take the derivative of f with respect to u, and then multiply that by the derivative of u with respect to x. Essentially, we're taking the derivative of the first function of the outside function first, f of u, f prime of u. That's what it says below here. And also multiply that by the derivative of the function u with respect to g. Or we can write it like this. So this is kind of the more two different kinds of notations saying the same thing. So the first thing, take the derivative, essentially what's called the outside function, okay, derivative of f first, and then take the derivative of the inside function g. Okay, and it kind of says that below here. I mentioned that since we have a function within a function like a composite function, essentially take the derivative of the whole thing. Let's put in this more normal words. Since you take the derivative of the outside function, then go inward. So keep taking the derivatives. And also, if the function g itself, the inside function is also a composite function, you have more functions within function than just two, then you essentially keep on repeating the chain. You keep on multiplying the derivatives together. And we'll see an example like that later on. So let's practice with this sum over on the right side. Let's do some examples. So let's say our directions be to find the derivative. Let's take a look at some basic ones first. And the first one let's start with is this. So let's say we have, let's say f of x or y is equal to, in parentheses, 3x minus 2. Let's say this is to the 7th power. Now, if it was squared, that would actually be pretty easy to do, because you could just use the techniques we used before, just multiply these 3x minus 2 quantities squared, just FOIL that out, and basically turn into something that's kind of a nice linear form and take the derivative of each part. You could also multiply this out, but obviously it would take a really long time. You don't want to do that. So we're going to use the chain rule for this. So what that means is that the derivative of, so essentially this on the inside is essentially my g of x. Okay, so let's take the derivative. So f prime, the derivative of this, you write it is this form or another form of this, of f of x. Okay, so first the outside function is something to the 7th power. Okay, so remember what that means. It's just like this, which isn't a set of 3x minus 2, but it's just x to the 7th. That would be 7 out front. Then this thing right here, 3x minus 2, then you reduce the power by 1, 6. That's the first part of the derivative. That's essentially the derivative of what's called the outside function. Okay, essentially that's the derivative of our f of x. Now work on the inside, then go inward. What's the derivative of 3x minus 2? You multiply that, and the derivative of that is going to be just 3. Okay, derivative of 3x is just 3. The derivative of minus 2 is 0. And so we put all this together. Of course, 3 minus 0 is just 3. We can simplify this, make it look better. It's going to be 3 times 7, or 21, times 3x minus 2 is 6. Okay, so that's our derivative using the chain rule. And that's the same thing. Now, obviously, if you actually did multiply this all out, wrote it all out, a lot of terms, and then took the derivative of each one of those terms, it actually would be the same, but wouldn't be clear it was the same because you'd be all multiplied out. But this is how the chain rule works. Okay. Now let's actually take a moment and let's do the same thing here. Let's actually repeat this one. We'll do something called U substitution. This is something that isn't necessary, especially at this point, but often can be useful if you have a complex function trying to simplify it. So let's see if I can kind of put both these on they're on the screen at the same time. Yeah. So this is kind of using this idea we mentioned here already. It's kind of going backwards. So if we have some composite function or complicated function like this, where we have some function f, and then on the inside we have another function, it's often helpful to write the inside function as something called u. And someone just a long time ago picked the letter u. Of course, you can use whatever you want, but call it u so we can write the function like this, y equals f of u. And often this makes it easier to write a complicated expression in a simpler way. And often we get into other, later on in calculus, when we talk about integration, often that's one of the main techniques of integration to actually find the integral of something. And that's for the future. So let's repeat this one. So let's come back over here. I'll just say this is just another way of doing this. Okay. To use what's called U substitution. Reread that. Okay, so what we're going to do then, let's just write our function again. F of x is equal to 3x minus 2 times 7 to the 7th. Okay, when I say, I'm going to say let u equal the inside part, 3x minus 2. Okay, so now, so we can write this. So f of x then is actually equal to f of u, and this is just now just u to the 7th. Okay, there's what we have. So this is u to the 7th. Of course, now u, or u of x, is this. Now, how does that help us? Well, it makes it a little bit easier to see this, and especially work with this version right here of this statement. So let's do that. So first off, if I do the derivative of f with respect to u, okay, what's the derivative of that? Stray mark. Of f with respect to u, so that's going to be 7 times u to the 6th. Okay. Then if I do the derivative of u with respect to x, come up here, so u is 3x minus 2. We said that's just 3. And so we can say that the derivative of f with respect to x, just repeating this first line here, it just basically these multiply together, what we just did. So that's going to be 7u to the 6th times 3. Okay, and of course that's going to be 21u to the 6th. Now what I'm going to do now is substitute back. So I'm going to put this back, get rid of the u, put it back in terms of original terms. So u is 3x minus 2. And so then the derivative, and actually I meant to, hang on, I meant to write something else. Let me just expand this out here. I meant to put it as, so df dx is going to be derivative of f with respect to u times the derivative of u with respect to x, and that is this equal to, I want to make sure I include that part to make that clear. Just repeating this, okay? Now, put this back, and so what we have then is the derivative of f with respect to x is just going to be, as we said before, 21 times 3x minus 2 to the 6th power. Okay, and that's an idea called U substitution. It isn't necessary, but often it can be helpful, especially with a complicated term, to kind of see how to integrate, how to change it. Okay, let's look at another one. So number 2, let's say we have this. Let's say, let's call it f of x again, the square root of x cubed plus 2. Okay, now, remember what the square root is. We can also write this, if you want to write it as a power, and write this as x cubed plus 2 to the 1/2 power. And I don't think it's often easier to change it to that. All right. So the derivative You write it as f prime of x, or can write it as df dx. So the derivative of the outside function, the outside function is something to the 1/2 power. So remember, this works just like a regular power, so it's 1/2 times that something, x cubed plus 2, and then reduce the power by 1. So 1/2 minus 1 is negative 1/2. And then the derivative of the inside. Okay, so the derivative of the inside of derivative of x cubed plus 2 is just going to be 3x squared. And of course, the derivative of 2 is minus or plus 0. Let's put all that together, simplify it some. So we have, let's make a fraction here. So down here, remember that we move this down. So we have a 2. But down here, we also have x cubed plus 2 to the 1/2. Remember, if you get rid of negative exponent, moves it downstairs, down the bottom. And up here, we just have 3x squared. And then one last thing. Let's put this back in terms of a root. And so this is going to be 3x squared times 2 down here, then times the square root of x cubed plus 2. And that's our derivative of that function. And once again, that's just using the chain rule. Well, this allows us a good way to understand how to take the function, how to take the derivative of a more complicated function. Okay, let's see what we want to do next. Do see what we want to try next. Okay, how about this one? This time, once again, it's called f of x is equal to the sine of x squared. Okay. All right, so once again, what we want to do is we'll go from the outside in, start with the outside function, work in. And so df dx is equal to, so the derivative of sine is cosine of something. Derivative of sine of something is cosine of something. So if this is just the, without the square, just the x, it should be the cosine of that. So the cosine of the something is cosine of x squared. Then times the derivative of the inside function. The derivative of that is just going to be 2x, and we'll just bring the 2 out front. And so this is going to be, or bring the x out as well, doesn't matter, 2x times the cosine of x squared. And that's the derivative. So this is also going to write this as f prime of x, or write this as df dx. All right, now let's do one more thing. Let's also find the second derivative. So we're going to write the second derivative. It's the derivative of what we just did. As f double prime of x, or you can also write this other notation as, this is called differential notation, if I haven't mentioned that before. D squared f over dx squared. What that means, we're just going to take the derivative of this whole thing. Now, if you notice here, this says two functions of x multiplied together, so you have to use the product rule along with the chain rule. Okay, so a little more going on, but that's okay. So d squared of f dx squared. All right. So remember, the product rule is easy to remember. You just take the derivative of one function times the other function, plus then switch it back. So take the derivative. So take the derivative of the first function times the second function, plus the derivative of the second function times the first function. And it doesn't matter which one you call the first or second. That's the great thing about the product rule. The order doesn't matter. So let's say take the derivative of 2x first. That's going to be 2. Okay. Then just times the second function, which is cosine of x squared. Okay. Then plus, now we switched up the derivative of the first function, 2x, times the derivative of this function. Now we have to use the chain rule here. Okay, so it's just almost exactly like what we just a minute ago with the sine of x squared, cosine. So if you remember, the derivative of cosine of something is negative sine of something. So we negative sine of x squared, then times the derivative of x squared, the inside function, which is, of course, 2x. And then let's put all this together, simplify it. All right, so it's going to be 2 times the cosine of x squared. And it looks like we kind of thing, we're going to have a minus, and then 4x squared times the sine of x squared. And that is our second derivative. Okay, and of course, you can also find a third derivative if you want. Just be more complicated again, but you have to take the derivative of this. So you can keep going as many times as you want. All right. Let's see, I believe this is up to number 4. That's number 4. Okay, for number 4, let's take a look at this one. Let's say we have the cosecant of 3 times the sine of x. Now, one thing I want to mention here is you have to be careful. Remember, cosecant and sine are inverses, but that's not what's going on here. This isn't the cosecant of x times the sine of x. This is what you're taking the cosecant of is the sine of x itself. So those inverses rule does apply. So these don't cancel out or anything here because this isn't the cosine of x times the sine of x. Okay, your input for your cosecant is this. So once again, use the chain rule. Now, cosecant maybe one you may not remember that much. So if you look back your notes, that's fine. All right. Once again, take the derivative, and this should have wrote this is our f of x. So df dx. Okay. So the derivative of cosecant is negative cosecant times cotangent of whatever this is. Okay, let's do that. So it's going to be negative cosecant of the something, which is 3 times the sine of x times the cotangent of the something, 3 times the sine of x. And then finally, take the derivative. So that's the percentage derivative of our outside function. Now the derivative of the inside function, 3 times the sine of x, of course, is going to be 3. And then the derivative of the sine of x is cosine of x. Okay. And also make sure it's clear we're taking the cotangent of this. So here, let's do one more thing. Let's just pull the 3 out front. So we have negative 3. I'm also bringing the cosine of x out front as well. And then here, this is times, then the cosecant of 3 sine of x times the cotangent of 3 times the sine of x. Okay, so that's our derivative. All right. Number 5. Okay, let's take a look at this one. So this time our f of x, our function is going to be e to the negative x squared. And e to the negative x squared is something you will, if you go into more math and science, something you'll probably see again that particular term in the future. But let's think about this. So we're going to do this a couple ways. We're going to bring in the u substitution again for practice, or may do that in this one, or maybe the next one. So if we have this, then, all right, so the derivative. So the first thing we have is e of something, okay? So the derivative of e of something is just e of something again, all right, of the something. So start with the derivative of the outside function is e to the negative x squared, then times the derivative of negative x squared, and that's going to be negative 2x. And actually, that's it. So we just make it look a little bit better. So negative 2x times e to the negative x squared. Okay. All right, number 6. How about we have this? Let's say we have this time for f of x. What about this? E to the cosine of x. It's kind of an unusual one. Now this time, let's actually use the u substitution on this. You don't have to. I could do it both ways. So df dx. So in the same way, the derivative e to the e of something is just e of something again. So e times cosine of x. Then the derivative of the something. Okay, the derivative of cosine x is negative sine of x. And so this is just going to be negative, it doesn't matter which one I write first, but I'll just write sine of x times e to the cosine of x. Now, this one, let's also use u substitution again. Let's also do it, make sure you get the same thing. So this time I'll say let u equal cosine of x, okay? So what we have then, our function f, now it's kind of a function of f of u, which is still a function of x, is going to be So replace the cosine with u, so e to u. Okay, then u is the cosine of x. So if you take the derivative separately, once again using this rule here, df du, the derivative of f with respect to u is our independent variable. So the derivative of this with respect to u is just e to the u. If we take the derivative of u with respect to x is the independent variable, the derivative of cosine is negative sine of x. And then say, so df dx is equal to df du times du dx. Put both of them together, e to the u times negative sine of x. And yeah, if we just move things around, also we'll put also say here we're going to substitute back, meaning replace the u, put back in terms of x. And so this is going to be df dx, as we just saw, negative sine of x times e to the cosine of x. Okay, so that's a little practice. Once again, using use of substitution, often it can be very helpful to do that. Okay, let's do one or two more. And what number am I on? I'm on number 7. Okay. This is going to be a little bit different. So first, let me write it out. So this is going to be sine, similar to one we've already seen. So a sine of e to the x squared. So we've seen e to the negative x squared. We've also seen sine of something. Now we put this together. Now, the reason I'm showing you this one is because this one we actually have to use the chain rule more. So what I said here with the chain rule, this last statement, if the inside function is a composite function, basically continue the chain in the same way. Okay. So this also means might kind of work your way outside from the outside inward for your functions. Okay. So let's go back and do that. So wait. Strange. All right, let me get back to where I was. Right here. Okay. So df dx, okay, is equal to, so work from the outside inward, okay? So this derivative of the sine of something is the cosine of something, and the something is e to the x squared, okay? Now, the derivative now is working inward, inside. The derivative of e to something is just e to that something times e to the x squared, okay? So we saw that just like a minute ago, but notice we're not quite done. You still have to take the derivative of x squared. So this one actually has 3 parts to it, but it works the same way, okay? So first is derivative of the outside function. Then next, move inside, the derivative of e to the x. Now the derivative of x squared is 2 to the x, okay? So that involves 3 parts, but no matter how many parts you have, no matter how many layers of functions you have, you just work from the outside in and just multiply each derivative times the previous one. Okay, this time we had to take 3 derivatives, and that's okay. So now if we just write this a little bit differently, I'm going to write it as 2x times e to the x squared times the cosine of, times the cosine of e to the x squared, and that's our derivative of that function. Okay, now let's do one more example. This one's going to be a little bit different. I want to mention here is for number 8. I might go over here. Not sure what's causing that. All right, number 8, what we want to do is still take the derivative, but use the product rule. Just read that. Instead of the quotient rule. Okay. The reason I like to do this, the quotient rule is kind of hard to remember, mainly because we're subtracting with the quotient rule. And of course, then if you're subtracting, anytime you're subtracting, order matters. It's kind of hard to remember exactly which way it goes. This form is much like the product rule, but it's harder to remember. So what I like to often do is actually use the quotient rule, the product rule, instead of the quotient rule. That's how you may have seen this. I mean, you've seen me do this in the previous video. That's before I actually talked about the chain rule. So the chain rule helps us out with this. So if you look over here to the left, you have a quotient, some function f of x divided by g of x. Okay, take the derivative of that. You can use the quotient rule. You can also, what you can do is you can write this f of x over g of x like this, as f of x times g of x to the negative first. Okay, so g of x to the negative first instead of putting it in the denominator. Then I can use the product rule of both these functions. Of course, the product rule is much easier to remember. Then, of course, doing that with the negative one, then I have to use the chain rule to help me out with that. To actually take the derivative. So let's do that. So let's call this function, let's call this h of x. Let's call it f of x. Let's just do it this way. And so let's do something fairly basic, don't get too detailed. So x squared plus 3 over 2x plus 1. Okay. Now, what I do then, I can write this also as x squared plus 3 times 2x plus 1. 2x plus 1 is to the negative first power. If these are equivalent, these are the same thing. Okay. So now, h prime of x, I can use the product rule, which is much easier to remember, as we'd already done before. Just take, it doesn't matter which, once again, the nice thing about it, doesn't matter which order, but I'll say take the derivative of the first times the second function, and then take the derivative of the second function times the first. Okay, so the derivative of this function, of course, the derivative constant is 0, so the derivative of this function is going to be 2x times the second function, which for right now is still 2x plus 1 to the minus 1. Okay, then plus the first function, not the derivative, just the first function, x squared plus 3 times the derivative of the second. And so now is where we're bringing the chain rule. So something to the negative first power is going to be negative 1 times something, 2x plus 1, to, remember, subtract 1, so negative 2 times, so you're almost out of space. I have a bit more over here. But subtract 1 from the power, that becomes negative 2 times the derivative of something, derivative of the inside function. In this case, is just derivative of 2x plus 1. Remember, the derivative of constant is 0, so derivative of 2x is just 2. And now, let's simplify this sum. Let's make it look better. Okay. And also what we're going to do is also get rid of our negative exponents. That's often something you want to do when you simplify. Also make that plus look better. Okay. So this first term is going to be 2x over 2x plus 1. Also remember those 2x's don't cancel out there. And here, we're going to have a negative 1. So this becomes a negative. A 2. In the numerator, we have a 2. And also an x squared plus 3. And then down here, we have our, sure that parenthesis right here, 2x plus 1 to the second power. Now, the only difference between this and what you get with the product or the quotient rule, the quotient rule puts it over one common denominator. So if you added these two terms together, put them over one denominator, which would be 2x plus 1 squared, simplified, you get exactly the same thing you would with the quotient rule. This just to me is another way to do it, which I prefer myself because it's much easier to remember the product rule than the quotient rule. Okay, let's review what we did. So today we learned how to take the derivative of complex functions or composite functions using the chain rule. We also learned how to do U substitution, which is often helpful in trying to simplify and rewrite a complicated function to make it easier to work with. And also we learned how to do an alternative to the quotient rule, which is actually using the product rule along with the chain rule, writing the function, writing the denominator as that term to the first power and using the product rule. Thank you. Have a good day.